Let's take a look at how to do a hierarchical regression in R. Now, a hierarchical regression is essentially a set of models where we are adding one or more regressors to the model at each step or block. And so this will actually involve running several models one at a time, building it as we go, and then comparing those models. And then we can get some statistics that usually get reported with the results, such as change in R-square from one model to the next. So I'm going to go ahead and take a look and make sure everything that I want is here. So I have car, and because we're going to use a data set from car, and we'll use the S function to get our summary of our results. We have, let's see, LSR is loaded as well, and psych is not yet loaded, so I'm going to just click that, load that up. Okay, let's go ahead and get our data set. So our data set is called UN98. This is a data set from the United Nations in 1998, so that makes sense. Let's take a quick look. All right, so this is a pretty big data set with many variables. We have pretty much all the countries in the world, 200 and something. But you'll notice that there's a lot of missing data here. And so we're certainly not going to have 200 and whatever cases for the regressions that we run. And that's going to be a bit of an issue that we'll talk about in a second. So the thing that we're going to try to predict here is fertility rate, total fertility rate. So that's how many children the average woman in that country is having. And then we have a few different things here, whether or not they're using contraception, the education level of males and females, the lifespan of males and females, the infant mortality rate, and some other things. But we're definitely not going to use all of these, although you could. We're just going to focus on a few things here. So what we're going to do, I'm actually going to add a script just so that we can do this a little properly here. And so this is just the plan. So what we're going to do in step one is we're going to look at the life expectancy. So we're basically we've got TFR is our Y variable, and we have the life expectancy for males will be X1, and life expectancy for females will be X2. And in the second step, we will add in education. So this is going to be X1 plus X2. So we're keeping the original two variables from step one, but we're now adding in education male, which is we can think of as X3, and education female, which is X4. And then in our final step, we want to see, let's say that our main hypothesis is that contraception helps predict fertility rates even after accounting for male and female life expectancy and education level. So this is all the previous variables, X1, X2, X3, and X4 plus contraception, which is our fifth and final regressor. Okay, so that's what's going into our three different steps. Now we're actually going to run a simultaneous regression first, and that's the regression with all five of the variables in there, and I'll explain why in a second. Simultaneous regression is what we've been doing up until this point. So in order to do this, we basically just have to create a full regression. we're predicting or trying to model fertility rate as a function of all these things. Life male plus life female plus education male plus education female plus contraception. I'm just going to hit enter here so that it doesn't run off the side of the screen here. And then our data is from UN 98. So that's that. So I'm going to go ahead and run that. So now we've got SimMod here just sitting around waiting to be tapped, and we can get a summary of the results here. So what we see is that 3 of the 5 variables explain unique variance in total fertility rate above and beyond all of the other 4. And so life expectancy for males, life expectancy for females, and contraception all are uniquely contributing to the estimation or the prediction of fertility rate above and beyond all the other 4. We have a really high R square, 0.87, and that is definitely significant. P is way less than 0.001. Now this is the full model. Notice that it's actually also our final step in the hierarchical regression that we are going to do. But a couple of things about that. So whenever you run a hierarchical regression, that your last model, your final step, whether that's a step 2 or step 3 or 4 or however many steps you have, the very last one is essentially identical to the simultaneous regression because it's a model with everything in it that you plan to include. And this also means that if you're interested in one variable above and beyond all the other 4 in this case, and that's really all you're interested in, then there's no real need to do a hierarchical regression. You can see from this result here, for example, that contraception does predict total fertility rate above and beyond all these other 4 variables significantly, such that holding all these 3 things constant, if you had 2 countries that had the exact same life expectancy for males and females, the exact same education level for males and females, but one country was 1% higher in usage of contraception, then that country with greater contraception use would have 0.033 fewer kids on average per female. So you wouldn't need to do a hierarchical regression in order to test that. But if you're interested in the impact of life expectancy as a set, because these are separated by gender, and then education as a set above and beyond life expectancy, then these first 2 steps would give you that kind of information. One thing that I'm going to do real quick is just use the JTools function in order to get our partial and semi-partial correlations. So I'm actually going to do this up here. I'm really only interested in the semi-partial. And so we're going to get the JTools package in the game, and we're just going to do pretty much the same thing we did with the capital S function, but this summary function allows us to ask for partial and semi-partial correlations. So I'm going to run that. All this is the same. If you go back through, you'll see that these numbers here are going to match these numbers here, just displayed somewhat differently. But what we're interested here is the semi-partial correlations, because those help us compare all of the regressors to see which ones are contributing more relative to each other. So this is more precise than looking at p-values, and we already know from many times we've talked about how we can't compare these numbers to each other because they're on different scales. So when we look at all these things, we see that 2 of the 5 seem to be doing the most job in predicting above and beyond everything else, and that's life expectancy for females, with countries with, on average, older females having fewer children, and countries with greater contraception use having fewer children. So those 2 are the most powerful. Life expectancy for male is a little bit lower, and then way down here is education for males and females. Now, just a quick note that you need to square these if you're going to talk about these numbers as representing the proportion of variance that gets added by including that variable on top of all the others. So the unique contribution to explaining variance, in order for you to use that lingo and to think about them almost as like our square additions to the rest of the model, then you do need to square these first, make them squared semi-partial correlations, and just break out a calculator to do that. Okay, let's get on to the hierarchical regression, because this is already a little bit of a long video. So what we're going to do is step 1 of the hierarchical. And you'll see that I'm going to basically copy and paste all of this, just so that I don't have to retype it all. But for step 1, I'm just going to change this so it says step 1. So that's the name of my model. Just keep things straight. And the only things that are actually in step 1 are the life expectancy variables. And just keep this down here. I could move it up, but now, if I run this, it's actually going to give us more data. Right now, these results we had were based on a certain subset of data. We had 62. If we take 56 and add 5, we get 61 plus 1. That's how, remember, that's how that we can add all this up to see what our total sample size is. If I run this like this, it'll run, but it's going to be a larger sample size because with only 3 variables in the model, there's less missing data to kind of cut away or eat away at our sample size. And that's fine if this is all you wanted to do, but in order for us to ultimately compare step 1 to step 2 to step 3, they all have to have the same cases in the regressions. In other words, we need to base our sample size based on the final step, which is going to be the smallest one in terms of our sample size, not because we like small sample sizes, but because as we go from 1 to 2 to 3, with all the missing data that we saw here, our sample size is going to get winnowed down and down. And if each of these steps has different sample sizes, they can't be compared to each other. So we need to take the sample size from step 3 and apply it to step 1 and 2. Now, in order to do that, I'm going to basically tell R to, hey, go back to this simultaneous regression, which remember is identical to step 3, and use that sample size, that subset of the data set. So this data equals simmod $model, a little bit sort of funky, but basically it's just saying use the subset of your data set from step 3 in running step 1 here. That'll keep all 3 steps. We'll do this again for step 2. It'll keep all 3 steps the same in terms of sample size. So I'll go ahead and run that. And we can see here that we just have the life variables in here. They're both significant. R square is significant at 0.77. Now we can do step 2. And I'm going to just copy this again. Copy and paste is your friend. And you can see just using this R script is also your friend. Saves you a lot of time compared to just doing it line by line down here. And then of course you can save it and rerun it at a later time. So step 2, you just have to make sure that you're keeping tabs on what you want to be in there and what you don't want to be in there. So in step 2, remember, we were including everything except contraception. So I just cut contraception out, and we still want to keep the same shrunken sample size here just to be consistent. So we can run that, get the summary. And a couple of things have happened. Now our two life expectancy variables are still significant. Education for males is not. Education for females is marginally significant. It's above 0.05, as you can see, but below 0.10. The R-square has bumped up from 0.77 to 0.808. Still quite significant. And now we can do step 3. Now we actually don't have to, because we already did step 3, as I've said a couple times in the simultaneous regression, but just to be consistent, and so we have a model out there called step 3. This is redundant with what we've done, but just a little bit cleaner, so that when we compare these models, we can just call them step 1, step 2, step 3. Now I don't really need to change this to be the same as sim model, because what we did before is the same. It's the same thing. But again, just to be consistent, I'll do that. Don't need to take out any of the variables because we want all 5 of them in there for step 3. And we can run this. We know exactly what we're going to see because we've seen it before, right? All 5 variables. The R-squared has gone up from 0.808 to 0.8715. So we started out in step 1 at 0.77. Then we went up to 0.808, so about 0.3 addition in R-squared, 0.03 I should say, and then up another 0.04, I think. No, that's more like 0.07, 0.06, 0.07. We'll get the exact values in a second. Okay, let's see which of these models, if each of these models is actually significantly improving the explanation of the Y variable total fertility rate above and beyond the other ones. This is pretty easy. We just need to use the ANOVA function because each of these tests is going to is essentially going to be an ANOVA test comparing each step to the next step. So step 1, step 2, step 3. So you just need to put in the names of the 3 models for each step. Actually, I'm going to do this up here. I forgot. This is tests of model improvement. Okay, run that. And we can see the residual degrees of freedom going down as we add more variables. And we can see the DF here. That's just how many degrees of freedom we've sort of eaten up. So we started with 59 when we just had 2 variables in the model. We had a total sample size of 62. In step 2, we added 2 variables, so we lost 2 degrees of freedom. So you can see how these 2 numbers here add up to that. And then in the final model, we added 1 more variable, so we lost 1 degree of freedom here, and it went over here. This is not the total number of degrees of freedom for the model. This is just the amount of change from the previous model. And then this is a test right here of whether or not the R-square has gone up a significant amount from step 1 to step 2, and it has. And then whether or not the R-square has gone up a significant amount from step 2 to step 3, and it has. So we know that both of these improvements in R-square are significant, but what we don't know is what the actual amount of change in R-square is. Now we have a general sense, and again, we could pull out a calculator and figure all this out, but why not let R do it for us? So the last thing that we will do is get our R-squared change values for step 2 and step 3. So in order to do this, we basically just ask R to compare those 2 values from each model. And so, for example, first we will ask for step 2 R-squared, and then subtract the step 1 r squared. And remember, that was when it went up from 0.77 to 0.80, so this should be about 0.03 something. And yeah, it's a little bit more than 0.03, a little closer to 0.04. So that's the improvement from step 1 to step 2. That's the r squared change. And then, I'm always in favor of saving some keystrokes. You can do the same thing and just subtract 2 from 3 to see how much better 3 is than 2. Remember, r squared can never go down. It can stay the same or it can go up, but it can never go down as we add variables to the model. Run that, and the bump up from step 2 to 3 is even better. It's about 6%, 0.063. That makes sense if you compare 0.81 essentially to 0.87. And that's it. That's the basics for doing a hierarchical regression in R. It involves a few steps, quite literally, but if you have a reason to do hierarchical rather than simultaneous regression, such as if you have sets of variables that go together, or if you have a variable that is categorical with at least 3 categories, which we will be talking about, then this is how you would do that.